Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. This is lecture 2. This is just a motivation for all of you that remember the expert in anything was once a beginner. There's always a first time to everything. So I hope you're excited to learn new things. Right, in the first lecture, I described NMR linguistically because to me that's the simplest way to actually understand on the concept. So today I'm just going to recap on that, perhaps expand a little bit on what this actually, the nuclear magnetic resonance spectroscopy are all about. Okay, now this is an interesting picture that I've put here. Now, in comparison to what I've shared with you last week, you have that really intimidating, gigantic geo spectrometer in Japan. So this is really a petite and small benchtop NMR, which is certainly going to be very useful for educational purposes and also for research purposes as well. I like the fact that it sits just neatly beside the analytical balance, and you can imagine how portable this is. So perhaps, as I put it here, we can call this really a disruptive innovation, or maybe a sustaining innovation of the NMR spectroscopy, NMR spectrometer or spectroscopy. Well, however you look at it, this is really a cool invention and a cool innovation. So something that let's hope that one day we have this in our lab. Right, nuclear, nothing fancy. It's just because we are focusing on the nucleus. And we also have another type of spectroscopy which focuses on the electrons. That's electron spin spectroscopy. And if you join the advanced spectroscopy class in the future, you'll be able to understand more on that. So back to the nucleus, there are 4 important physical properties, namely the mass, electric charge, magnetism, and spin. Now you know mass and electric charge, and you've learned that as part of your fundamentals probably in high school and also in your first year. But magnetism and nuclear spin is quite less tangible as compared to the other 2 concepts. So the magnetism of nucleus would refer to the fact that the nucleus interacts with magnetic fields like small ball magnet. It could be the magnetic field of the applied magnetic field, or it could also be the orbiting electrons that's creating magnetism with the nucleus. The spin of the nucleus is even less tangible. So the spin of the nucleus indicates that it is a much more abstract concept. It means that the nucleus is spinning around, rotating in space like tiny planets. It's really not an easy concept, but that's how we're trying to describe the spin. And so really the combination of this magnetism and spin is really the gist of what this NMR is, and that makes it such a powerful spying tool to actually decipher molecular the molecular environment. Okay, so this I've talked just now. So you know this I'm just going to just breeze through very quickly. You have this, you have the periodic table of the atoms and so on. Now well, you know that the mass number, and you have the, which is the total number of protons and neutrons, and isotopes are when you have similar atomic number but different mass number. And what I'm going to talk here, so those are just basic. Okay, so spin, let's talk about spin. The symbol for spin is I. So this nuclear spin quantum number depends on the angular momentum. Okay, for example, we have hydrogen, which has a single proton, and it has I equals to half. So the spins of other nuclei, it can also have, is formed by combining other spins of the protons and the neutrons. Now, you can have deuterium, for example, and it has a spin number of 1. So how do you decide whether it's going to be 1 or half? Well, there's a general rule. I'm not going to emphasize on this so much, but the even mass numbers have integer spin, and those with odd mass numbers will have half integer spin. Okay, and if the numbers of protons and neutrons are both even, you have I equals to 0. So examples of that will be carbon 12, which has 6 protons, 6 neutrons, and there's oxygen, which has 8 protons and 8 neutrons. So when you have I, or spin number, equals to 0, it's going to be NMR inactive. So only when you have, when I has a value, when you have a nuclear spin number, so you can actually have an NMR signal. So this is an important table which shows selections of nuclear isotopes. So for example, you have proton with a spin half and has a natural abundance of 100, and this is a gyromagnetic ratio with a symbol gamma, and this is has the largest value. So this is 267 times 10 to the power of 6, and with all these units, and this is the frequency at 11.74 Tesla. So if you look at carbon 13, so this we're going to talk mainly on proton NMR. We call this hydrogen 1, we call it proton because it's only one proton. So, and then this carbon 13 also has a spin of half. So carbon 12, as you can see here, has no spin number, and this oxygen system has no spin number, so that's why there's no NMR signal for this. So when this nuclear state, okay, has a spin of spin I, it will have 2I plus 1 for energy levels, equal levels of energy. But as soon as that is in the absence of magnetic field, but as soon as you apply the magnetic field, the degeneracy is broken, so it will not be equal anymore. The energy level is going to split, and that splitting is known as the Zeeman splitting, and it's named after Pieter Zeeman, who was also a Nobel Prize in physics in 1902. Now I should have added him in the list of Nobel Prizes related to NMR when I talk about the NMR related Nobel Prize last week, because certainly this is very important in NMR spectroscopy. Now this is just a trivia, it's just my curiosity, you know. The effect, I've just told you that the effect of splitting spectrum lines by magnetic field is called Zeeman effect, but if the splitting is caused by an electric field, it is called the Stark effect. So when I first found this, I thought, aha, maybe that's why Stanley named him Tony Stark. It's probably after this Stark effect. And when he was alive, I actually asked him in his Facebook page, but unfortunately he didn't reply, and he passed away soon after that. So really, you know, we never really know. I never really know, but it would have been cool if he replied my Facebook question. But I have this, you know, strong belief that that's where the name actually comes from, and I happen to be and Iron Man is my favorite Avengers anyways, so that's the coolest guy on earth. Anyways, okay, enough of the trivia. Now, so this is an example of the nuclear Zeeman sublevels. You have here the proton, the what do you call, the nitrogen 15 and the aluminum 27. So they have, this one has a spin based on the table that I showed you just now. So the spin is half, spin is half, and spin is 5 half. So they will have two I plus 1 levels, right? So this will have 2, 2, we have 1, 2, 3, 4, 5, 6. Okay, so this is an example of the Zeeman splittings that I mentioned to you. But here's a question for you. If I were to show you this, what's the obvious question that you should ask when you see this? I'll give you about, 3 seconds. What's the obvious question you should ask when you see this diagram? Right, I hope you realize that the obvious question is, if this is half and this is half, why on earth is the splitting small? Okay, so why is this small and why is this big? Why do you think? Give you another 1 second to think. Well, if you look at the table, okay, it's because of the values of the energies, the values of the gyromagnetic ratio for proton is much larger, and so that's why it's large. So then something for you to think about is that you can actually sort of like gauge the equation for this energy splitting based on this. All right, so we've seen that you have the tables having different values of nuclear spin, but you also have some which has 0 nuclear spin, and so they are NMR silent or NMR inactive. Okay, so now magnetic. Now I mentioned probe as a verb when I said that NMR is a good spy and it will probe the molecule, and that when I use the word probe, it is as a verb. So now I'm using the word probe as a noun. So this is called a probe. This is a thing called a probe. So this is where inside this you actually put the NMR tube. Okay, and it goes to the middle of the magnetic field, and then the sample is inside the probe, as I said. And one of the things you want to make sure is that the magnetic field needs to be homogeneous and stable, so you have to tweak some of the parameters on your computer to make sure that it's stable, so you have a sharp peak here. So as I said, this is where you'll be sitting comfortably, controlling the parameters. You can see here pictures of FID and then Fourier transform to the NMR spectra. So this is the machine, this is the electronics here, and you've seen this before, and I also hope that you have watched the video to understand how the NMR is conducted, although that's really an old school video, but the concept, the way it's done, is still the same, though it might be a little bit it might be, you may have sophisticated machine, but the concept is still the same, and you still have this superconducting magnet being protected by the liquid nitrogen, and on top of that being protected by the liquid helium. Okay, and so this is an example where you are the people in the lab actually refilling this. I don't have the picture of our own people refilling the lab, so hopefully one day I get to take our own people's pictures of them refilling the, not refilling the lab, refilling the gas, liquid, the liquid nitrogen, liquid helium. Alright, so the probe itself contains the radio frequency coils and tuning at specific frequency for specific nuclei. So when you tell it at the computer you want to look at protons, so then it would tune to the specific frequency for that nuclei. If you're looking at, for example, carbon-13, then it will actually tune that. Okay, and sometimes you need to change the temperature. So especially if you're working with solid state NMR, we can actually do that, but rarely for the liquid state you actually change the temperature. And I've done that once for my own liquid crystal samples on the liquid state, and right after that, nobody wants to actually run the experiment after I've run the experiment, because the tuning went quite off. Because with liquid state, it's usually done at room temperature. Okay, so the principle behind NMR is that many nuclei have spin and all nuclei are electric charge. If an external magnetic field is applied, an energy transfer is possible between the lower state, the higher state, and at a wavelength that corresponds to radio frequency, and then it returns back. So this is the concept of resonance. So as I said, that the signal matches when you have this transfer from lower level to higher level, the radio frequency that is actually applied matches that. So then you have that transfer, the jumping of energy from lower state to higher state. So that's where the resonance comes in. So now this is what we're going to cover in the next class, and you've seen it before. I'm showing it again. So again, remember I mentioned about degeneracy. So this is when there's no magnetic field, so you have all the energy levels being equal. But as soon as you apply the magnetic field, so you have here the what you call the Zeeman splitting. Now, one of the things that you saw just now, that the difference between the proton and the nitrogen 15 is that what's different in the delta E, the energy levels, the energy splitting, the fact that the proton has bigger splitting is due to the value of gamma. So that's why I asked you, so you can actually gauge from that, even before I show you this equation, you know that this delta E has to be dependent on the gamma. The other thing that it certainly has to be dependent on is the how big is the magnetic field, and then the next one is a constant, which is the h bar, the Planck constant over 2 pi. So this is the lower state and the higher state. So this is what we are going to talk a bit next week. So this is just a teaser for you. Alright, so I'm going to leave you with these questions for you to just answer. So if you really understood what we have covered today, you should be able to answer these questions. So what does NMR active nucleus mean? And why are the Zeeman splittings for proton and nitrogen 15 different, even though they both have spin I equals to half? What are the roles of liquid nitrogen and liquid helium? The stronger the magnet, the complete descendants. This could be anything that makes sense. Now, I do want to give you a piece of advice. Well, these lecture notes are of course important to you. Don't make this the only source of references. There are a plethora of information. You can, like as I said, a good textbook or something is very important. So but the gist will be from here, and just stretch your mind and learn a bit more. So there's so many bits of NMR to actually learn. So I'm just sharing with you the fundamentals, the basis, and that's what I hope you get out of this. This 14 weeks to know a little bit more on NMR, the concepts, and what it means in terms of theoretical, in terms of why things are the way it is, and so on. Okay, to appreciate this as a very powerful tool. All right, so that's all I have for you today. So till next week, so take care. All right, thank you, and assalamualaikum warahmatullahi taala wabarakatuh. Bye for now.